Assalamualaikum warahmatullahi wabarakatuh and good morning to you guys. How are you guys? Can you hear me? No response?
Yes, Doctor.
Morning, Doctor.
Morning. Okay. Assalamualaikum warahmatullahi wabarakatuh. Okay. It's already 10 a.m. We will wait for further 2 more minutes. Then we will proceed with our lecture today, which is the topic on distillation. So we're waiting for them. Any questions? No questions? Okay, your test will be this coming Tuesday at 8 p.m. You will be able to view the questions 5 minutes before 8. And you are only given 1.5 hours to complete the 2 questions. If you don't have a printer or you don't have any way of doing using the graph provided, then you have to plot it yourself using your own graph paper. But the data, you will have to get it from the appendix. They are not given in the question. Besides that, the time set for you to complete, you are only given 10 minutes. Not mistaken. I'll get back to you guys on that. Anyway, I will give you guys the instruction by Tuesday. Okay, the question will be set in e-learning. You have to submit the questions, the solutions, your solution in e-learning. But if you're having difficulty, can submit it to me by email. Hope you guys know my email. Or the last resort is to use WhatsApp. Besides that, the question, they are very straightforward. I don't see any difficulty with the questions. So any questions on the test?
So Doctor, I have a question. So Doctor, do we submit the question in one PDF only, right? No need to split the question.
No, just one PDF.
Oh, okay, thank you, Doctor.
Anything else? If there's nothing else, there's no question on the test, we'll now start to look at distillation. So I will stop sharing the QR code. I will share it again towards the end of my lecture. So right now I will start to share my notes. I hope you guys already managed to get the notes from e-learning. There's 2 parts to it. It's quite a long topic. It's a big topic, distillation. This is you will be tested on distillation in your second test and also your final. For the second test, the distillation, the topic on distillation will be tested on MACAP and Thiel method. But your final will be on multi-component distillation. Okay, so let me record first. Okay, distillation. It's nothing new to you guys. You guys have come across it before. Okay, distillation is the most common types of separation in the industry. Sometimes you do distillation before the reaction. Sometimes you do the reaction after the reaction. Okay, so it is the most common, and unfortunately, it's the most expensive to maintain. It consumes a lot of energy. It's for the cooling and the heating up of the distillation, for the heating of the reboiler, and the cooling in the condenser. So distillation is a very energy consumed unit. Yeah, so how is it based on? The separation is based on the difference in the boiling point, or volatility. If you have two components, for example, ethanol and water, ethanol has a lower boiling point compared to water. So as long as the difference in boiling point is quite a lot, you can easily distill it. If it's too close, it gets more difficult to distill. Most of the most common type of distillation that we come across is petroleum refining. I think there's a spelling error here. Okay. Petroleum refining. So when you heat up the well, in this diagram that I have over here is a distillation column, the schematic diagram. That is rectification or fractional distillation column. Your feed is coming in here. Could be liquid, could be gas. If it's gas, it should be coming from the bottom. It could be a mixture of liquid and gas, or vapor, sorry. So what happens is that when the liquid flows down, it gets heated up in the boiler. Okay? So the liquid will change to vapor and rises up. And as it flows upwards, now we are not looking at startup. We are already this is already a continuous process. This is already running. So when this is the vapor coming from the reboiler, there's also another liquid coming down from the reflux. Initially, the vapor that is rising up at the top of the column will be condensed in the condenser and changed to liquid. This is a total condenser. So you got your product as the distillate. This is your distillate. And part of that condensed vapor will be returned back to the column. And this will be your liquid. So the liquid over here will be in contact with the gas coming up through it. So there is equilibrium on that tray. Okay, the liquid that is on the tray will be in contact with the vapor passing through the tray. So there will be mass transfer there. Any of the component that has a lower boiling point, when it is in the liquid phase, it has a lower boiling point, it will vaporize. So it changes to vapor. But the component that is in the vapor, that is coming up in the vapor, that has a higher boiling point, when it touches the liquid is cooler, it will condense. So there's a process of condensation and vaporization on the tray itself. Okay? The lower boiling point will vaporize, the higher boiling point will condense. So as you go up as you go through each stages, the process will repeat itself until when you reach the very top, that vapor will contain the most will be richer. Let me change this. That vapor will be containing more of the lower boiling point component. Okay, it will be richer in the most volatile component. That means the lower boiling point component. And the liquid coming down here will be richer in the less volatile. That means the higher boiling point. Okay, this will have a higher component, higher boiling point component. And at the top product, you will have lower boiling point component. So that's how the separation is done. So this is only looking at two components. For example, you have ethanol and water. So there will be more of ethanol here compared to water, and there will be more of water in the bottom product compared to ethanol. because methanol vaporizes easier compared to water. It has it's more volatile compared to water. So there will be more ethanol in your distillate. This is referred to as distillate. And this is referred to as bottom product. Subscript W. Here you have subscript D. Okay, that's how the separation is done. Okay, so in this topic, the first part of it, you will be calculating the number of stages as how you have done in absorption. The operation itself can be done using pack tower, but in this distillation, we will concentrate more on stages. How to calculate the number of stages, how to calculate the number of trays. We are not going to look at pack tower, but it can be done. Distillation can be done in a pack column. Okay. So there's two types of distillation. Well, not really. There's a lot. There's more. Not only two types. Sorry. There's two methods of distillation. There's more than one. There's more than two types of distillation. There's two methods of distillation. The schematic diagram that we just looked at involve reflux. Reflux means you will return part of the condensed liquid into the column. That will enrich your product. Your product will getting richer or purer at the top, and you will get a pure, much more richer for a bottom product. Okay? So that's the advantage of having a reflux. And there's another type whereby instead of returning the condensed liquid, you will remove the vapor or the condensed liquid totally as product. You will not return it back into the column. So that's the two types of distillation. But the types of distillation, there's a lot. There's quite a lot of them. Simple distillation, you have flash distillation, you have steam distillation. They normally involve only single stage. These three types of distillation, they're mainly single stage. Okay, the others, they can be multiple stages. You have vacuum distillation, obviously that's vacuum is that it means it operates under vacuum. Extractive distillation, you have another solvent, another liquid coming into beside the feed itself. You have another liquid coming in as a solvent. So majority when it forms an azeotrope, then you will have an extractive distillation. You can read further on that. There's another molecular distillation. We're not going to look at that. We're not going to look at extractive or azeotropic, but we'll be looking mainly at this simple fractional steam flash equilibrium. We're not going to look at molecular, so we're not going to look at that. We're not going to look at azeotropic. So these are the four types of distillation that we will look at, but the majority of it will be in fractional distillation because that's what happened in the industry. You do have steam distillation, but because it's just a single stage, so it's a very simple types of distillation. So the other three, they are just simple stage. Okay, before you can do distillation, it's like when you were doing absorption, you need the vapor-liquid equilibrium relationship. When you were looking at absorption, the vapor-liquid equilibrium relationship was Henry's law. Now we'll be looking at Rao's law, and normally Rao's law is for an ideal solution, meaning that the substance, they are very similar to each other. For example, benzene and toluene, the two of them, they are hexagonal. I mean, they are of this ring type of, the structure is ring type. The only difference is that in terms of one of the attachment is different. So they are similar. So they are ideal. Okay? So in this Rao's law, the equation that we're going to look at, the equation is, this is your vapor pressure, not vapor pressure, sorry, partial pressure This is your vapor pressure. You are mainly interested in getting the relationship of Y and X. What is Y? What is X? Y is the mole fraction in the gas phase or in the vapor. X is the mole fraction in the liquid. Your component A is the one that is transferring. Because, for example, you have A and B. So component A is the one that is transferring in both ways, from liquid to gas and from gas to liquid. Condensing and vaporization, both ways. Alright, so the equation that we're looking at is the partial pressure of component A is equals to the vapor pressure of component A times by the mole fraction of component A in the liquid phase. Or there's another way of looking at it in terms of Y. This is your mole fraction in the gas, and this is your mole fraction in the liquid. So here you have your vapor pressure divided by the total pressure. This is your total pressure. And from this equation, you'll be able to come up with your vapor liquid data that you need to plot your graph. So normally, the data they are already given. You don't need to use the Rao's law to get the data. For example, in this case, this is for benzene and toluene. You have the vapor pressure here. This is your vapor pressure. This is your temperature, and this is your mole fraction for X and Y at one pressure. That means this is at a constant pressure. So you have your temperature versus your X and Y. You also have the vapor pressure. So the temperature versus X and Y is also given in this graph. This is your temperature. This is your X or your Y. So you got from this graph, you'll be able to see that there's two curves. The bottom curve is your saturated liquid line. That means at the very bottom here is completely liquid, a single phase of liquid. At the top curve, that is the top curve is the saturated vapor line. So anything above that saturated vapor line will be your complete vapor phase. It will be a single phase of vapor. But anything enveloped within the saturated vapor and liquid line, that is a mixture. You will have liquid and vapor. It's a mixture. So that is it's already written there, but I got it again. Okay, so this is your temperature versus XY plot. So for example, if you are looking at a temperature of what is it here? What temperature is that? About 95? About 95 roughly. So the liquid composition, is that, and the gas composition is that of your component A. And the two of them will be in equilibrium. So that means if you look at a tray, from here, this is your vapor coming out. So that vapor, for example, this is tray number 2, for example. So that vapor will have a composition of YA2. And the liquid that is leaving it, this is the liquid that is leaving it from that tray. So that liquid will have a composition of YXA subscript 2. So the two of them will be in equilibrium. So that's what you get from this graph. And at that temperature here on that tray, So the same thing will repeat itself. So again over here, you have the vapor there, you have the liquid coming down there. So it will be in equilibrium. So the saturated vapor line is also referred to as the dew point. The saturated liquid line is also referred to as the bubble point. So the difference between the liquid and the vapor composition is what we want when you're doing distillation. Because the liquid is coming down, so that will be your bottom product, and the vapor is going up, that will be your condensed vapor, your top product. So the difference in the composition is what makes the separation in distillation. Mainly, you will not be looking at temperature versus XY diagram. Sometimes you're also given the pressure XY diagram, then the temperature will be constant. Sometimes you're also given enthalpy XY diagram, but majority you are not dealing with the temperature XY diagram. All these three you are not going to do a lot of them, but most of the time you'll be looking at this diagram, which is XA versus YA. And if you look at this diagram, you will draw your mole fraction. The highest value is 1. The lowest value is 0. And you will draw yourself your 45-degree line, which is that diagonal line. That diagonal line is for you as a reference. The equilibrium value is the curve, which is this curve. That is the equilibrium value. So if you want to find, for example, the composition for the X, then you go towards the X-axis. And if you want to find the composition for the Y, then you go to the Y-axis. Or the composition in the gas phase, you go towards the Y-axis. And if you want to find the composition of component A in the liquid phase, then you go to the X-axis. In this case, you are looking at benzene, and the diagram is actually for a benzene toluene vapor liquid equilibrium. So the farther away is the distance of your equilibrium curve. This is your equilibrium curve, or equilibrium line, whichever you can say either one. The difference of the equilibrium curve from the 45-degree line, the easier it is to separate. Okay. But if it is at this 45-degree line, y equals to x, that value is the same. For example, if you look at this, it's the same. It's about, my diagram is not that good, but the way I draw my line. Let's redo it. Let's draw a proper line. But make sure that it is straight. It's not straight. Straight line. You can see that the value on the 45-degree line is y equals to x. They're the same value. So when y equals to x, no separation will happen. But when there is a big difference of the gap between the equilibrium curve and the 45-degree line, the gap is quite big, then separation will occur very easily. But the narrower it gets as it approaches the 45-degree line, the harder it will be to separate. So, but when it is on the y equals to x or on the 45-degree line, no separation will occur. For example, I have this diagram here, over there, and over here. At that point, your composition of your liquid and your vapor will be the same, so no separation will occur. So in this case, that's why you cannot go any further. You cannot proceed to get a much richer composition. For example, let me roughly give this value about 0.5. Okay? That's your x, and this one is about 0.5. So that is the maximum you can reach. The composition of your vapor, the liquid, they are the same. So you cannot get any richer than that. Your vapor that condense at the top product will not get any purer than 50% of the composition. Okay, 0.5 mole fraction. You cannot reach 0.8. You cannot reach 0.8 composition for the vapor or for the gas phase. I mean, for the liquid and also for the gas phase, you cannot get it any richer. So that means your bottom product and your top product, the majority is on the top product because you wanted it to be in your top product, because mole A, the mole fraction is majority for component A. Component A is the one that is the lower boiling point. There's two components, A and B. This one is lower boiling point. One is higher boiling point. So you wanted more of component A in your top product, but you can't reach that because you already your at that point y is equals to x. You cannot go beyond that point anymore. Okay, so the highest you can reach for your top product, the composition is only 0.5. That is referred to as azeotrope. In this case, it's referred to as azeotrope. So some of the example of an azeotrope is ethanol water. You cannot get purer than if you use distillation, you cannot achieve beyond when it form at y equals to x. At that point, you cannot reach get any higher. The composition cannot be any higher. And so that means if you want a pure product, you want a higher composition for your mixture, for your for example ethanol, then you have to do a different method of distillation, and that normally is done using extractive distillation. Not the typical fractional distillation, extractive distillation. When you have an azeotrope, or it's sometimes referred to as azeotropic distillation. So that's what you need to know when you have azeotrope. You cannot reach it any higher. You stop when it reaches the 45-degree line. An ideal solution, the curve is it looks like this. This is an ideal solution. Your equilibrium curve is the perfect curve. But when you don't have an ideal solution, how the diagram will look like is your curve will be not a perfect curve. That's for a non-ideal solution. But when you're looking at ideal, it will be perfect. Your curve will be a perfect curve. So you get your data using either Rao's law, in this case Rao's law, or there's another way to get your data, which is using the relative volatility. So far, any questions? Any questions? No? Okay, let's no. Okay, let's see whether we have any question on the Rao's law. Okay, this one. This is Rao's law. You need to find the composition of your vapor and your liquid at a temperature of 95. They should be in equilibrium. Okay. Given the vapor pressure, they are from this table, so that's the table. Okay, that's the vapor pressure. At 95, the temperature is 95. So if you look at 95, that's 95. And the vapor pressure for benzene in terms of kilopascal is that. The vapor pressure of toluene in terms of kilopascal is 63.3. So you want to find, actually you wanted to find that value for XA and that value for YA. But the table is already provided the values for XA and YA. But how do they manage to get it? They are using Rao's law, and Rao's law is YA is equals to vapor pressure divided by total pressure XA. Sorry, that is okay. That is vapor pressure. That is vapor pressure. But in order to get your, you can also get your YA using the partial pressure. That is partial pressure over total pressure. That is also Rao's law. So let's go back to our Rao's law. That is WXA equals to partial pressure over total pressure. or you can also have YA equals to partial pressure over total pressure. It depends on if you're looking at in the vapor phase, it should be in the vapor phase, isn't it? It cannot be in the liquid phase. That's a bit, let's see, I don't think that's correct there. That's correct there. Let me check on that. But this is correct. There you go, there you go. Okay, now that is correct. This side is correct. This side is correct. This side, I don't think it should be XA. I think it should be XA, it should be YA. Okay, so go back to the example. So your vapor pressure, that is your, okay, how to go there about here, you notice that this is your vapor pressure. Vapor pressure is capital P, sorry, subscript A, 155.7 kilopascal. So that's for benzene. So if you want to find YA, that is partial pressure, vapor pressure, sorry. I'm getting confused because I need to get the equation first. So over here, that is partial. That is vapor pressure. That is total. So YA is equals to your vapor pressure, 155.7 divided by your total pressure. In this case, the total pressure is 101.32 kilopascal, both of them. So that's XA. That's one relationship that you have, but one equation, two unknowns, that's not possible. But you do know that partial pressure A plus partial pressure B is equals to total pressure. But this thing is vapor pressure. You are given vapor pressure, not partial pressure. And where is the relationship of partial pressure? That is partial pressure. And partial pressure is equals to YA times by total pressure. So now what's next? Anybody? Any suggestion? Any suggestion? How to proceed? Anybody?
We could rewrite XA in terms of pressure.
XA. What is XA then?
Yes.
What is XA then?
It will be the partial total pressure over partial pressure. But it's the same. It's not.
Partial pressure over total pressure.
Yes, probably.
Partial.
We'll give the same answer. That is now possible.
What next? Anybody? What's next? Okay, this is one equation. So your partial pressure is equals to XA by total pressure, right? Is that correct? Is that correct, guys? So if I substitute
Yes, doctor.
Yes.
Yes, doctor.
if I substitute it over here, Is that partial? That is partial pressure. Is okay. Now for we should be getting this equation. That equation. Do you know how we get that? From the partial pressure. From the partial pressure, we're going to get that equation. Do you know how to get that? Anybody? Suggestion? Partial pressure of A plus partial pressure of B equals to total pressure. And your vapor pressure XA plus your vapor pressure of B XB equals to total pressure from this part. Because partial pressure, go back to the equation. The relationship. That's the relationship, sorry. Not total pressure. See, this is where I got, this is, let me get this correct. I'm confusing you guys. This is the equation. Partial pressure, that is partial pressure, is equals to vapor pressure. Vapor pressure. And this one, this is here. That is that. This is correct. This is partial pressure. That is total pressure. That is total pressure. This is vapor pressure. That's where I got confused just now. And this is partial pressure. That is vapor pressure. So when you do the partial pressure, this is partial. Let me put it over here. You have partial pressure A plus partial pressure B equals to total. So when you have that partial pressure, you substitute vapor pressure XA. Okay, vapor pressure of B. That's vapor, that's capital. This is small, lowercase. That is lowercase. That is partial. I got confused now. And this is vapor. That is vapor, that is vapor. Time by your XB equals to total pressure. So now you only have two components, A and B. So XA plus, let me put it this way. XB is equals to 1 minus XA because you only have two components. Okay? XB equals to 1 minus XA. So you substitute that over here. Okay? You will get vapor pressure of A times by mole fraction of A plus vapor pressure of B 1 minus XA equals to total pressure. Okay? Is that correct, guys? Still confused? Nobody going to answer?
Understand, doctor.
Okay, so that's what we got now. So this equation is the one that how we derive the equation here, the one listed here. That's the equation. That's the equation. Sorry, that's the equation there. Yeah. So once we manage to get that equation, so I'm going to put it here. And once we manage to put that equation, now all you have to do is you have your vapor pressure of A. Can substitute it there. Okay. Your vapor pressure of B, which is 63.3 kilopascal. You can substitute it over here. Okay. So you have the total pressure 101.32. So everything is there. Your answer will be 155.7. Your equation, not your answer, your equation will be 63.3. 1 minus XA equals to 101.32. So the only unknown is XA. Once you manage to get XA, then you will solve for YA using this equation. Is that correct? Let's go back again. I think I got a mistake there. Sorry, guys. YA, this is the equation that I made mistake just now. This is the equation. This is partial. This is total. Total. I already got it right there. I got it right there, but I wrote it wrongly here. In the example, I wrote it wrongly. That is wrong here. Sorry, that is wrong. Yeah, I got it correct. Why am I confusing myself? I got it correct. That's the total pressure. I got the total pressure there. I already got it right. Yeah. So that is the total pressure. So once you manage to get XA here, substitute your XA there, you should be getting your YA. So if you look at the solution here, from this equation, you get your XA. So your XA is this. Then when you substitute it inside this equation, then there, you get your YA. That's the value here, over here, and over there. Normally, you don't have to do this because the data is already provided. Right? So let me recap what I have done, because I think I'm kind of confusing. I caused confusion there. And so what you have to do is you have to find XA. This is YA. This is YA. XA and YA. Okay? Using this, the fact that partial pressure is equals to the sum of the partial pressure is equal to total pressure. That's the one equation. And the fact that you have partial pressure, you have partial pressure, that's partial pressure. And partial pressure. See, what did I do? I better erase this. Guys, partial pressure is equal to vapor pressure divided by total pressure. Yeah, partial pressure is equals to vapor pressure divided by total pressure. Is that correct? Confused because of no. I got confused again. XA, sorry. XA, I forgot. I keep on getting the total pressure there. Keep on getting wrong there. XA. Okay, there you go. Sorry guys, I keep on getting the mix up. Yeah, this is partial pressure. Partial pressure, that's vapor pressure. I keep on getting mixed up. Yeah. So when you substitute it inside this equation, it will be in terms of XA there. That's the XA there. These two, substitute here. Substitute there. Substitute there, you get this. And let me get it done better. Let me explain all over again. You have your partial pressure. Sum of it equals to total pressure. And over here you have your partial. This is partial. This is partial, which is the same as that partial. Okay, but this is also partial. Okay, but this is not partial. This is not partial. That is vapor. That's why I got confused just now between the P. There's two, one smaller case and one bigger capital P. Okay, so you substitute your this equation into this equation, you will end up with this equation or that equation. Your partial pressure, let me get it right again. Partial pressure is equal to vapor pressure. There's two P's, that's the problem. I got to get it. Okay, this is small p, okay, and XA. That will be clearer. And your small p, that's your partial pressure. This is partial to total pressure. So you substitute this part over there. Your partial pressure B is equal to vapor pressure capital P X B. Okay, so when you substitute that over there, you end up with partial vapor pressure XA plus this is capital B, so get it right. Now I got confused because of the capital and the smaller letter. Okay, there you go. And the fact that XB is equals to 1 minus XA, so you substitute that over here, you will end up with this equation, vapor pressure XA plus vapor pressure B 1 minus XA equals to total pressure. Get it right, the total, the small p and the capital P. I got confused there. Okay, so now you know that your values from the graph, from the table at 95, that is your vapor capital A, capital PA, and that is your capital PP, your vapor pressure. So substituting it inside this equation, 155.7 XA plus 63.3 1 minus XA, and the total pressure is 1 atm. That's the total pressure. So it's only in terms of XA, you solve for XA, and the answer is, if not mistaken, 0.411. That's the mole fraction. So once you manage to get that, now you can solve using YA equals to, there's another relationship, which is that relationship. Your vapor pressure divided by total pressure. Vapor pressure A divided by total pressure A, XA. So your vapor pressure of A is 1557 divided by total pressure. So your XA is 0.411. You should be able to get your answer for YA, and YA is equal to 0.632. Okay guys, sorry about that. A bit confusing there because of the vapor partial pressure and vapor pressure. A bit confusing because of the small p and the capital P. For me, it caused you guys to be confused. Okay, is that okay, guys? Any questions on that? Is that okay? Okay. Actually, you really don't need to do the calculation because the data is already there. These are the data that you need to plot your X and Y graph, which is that graph over here. This graph, your Y and your X. That's all you need. They're already in the tabulated form. Majority, they are already tabulated. Unless somebody introduce something, then you have to do the calculation. Then this is how you do the calculation. But that's a lot of calculation if you have a lot of temperature range, isn't it? That's one example. And the way to get your equilibrium data is using relative volatility denoted by alpha. Relative volatility is denoted by alpha. If you have two components A and B, then it will be having a subscript A and B. That means how you compare the relativity of component A with respect to component B. That's what it means, subscript A and B. How easy is component A compared to component B in terms of relativity? In terms of volatility. Volatility. How easy it is to vaporize. So this is the equation. And if you get relative volatility equals to 1, then no separation will occur. It should be greater than 1. Then it's possible. Again, if you are using an ideal system that obeys Raoult's law, this is what the final equation you will get. How to get your Y and your X in terms of the relative volatility. So this is the equation for Raoult's, using Raoult's law. And if you want to look at the values of relative volatility, for example, benzene and toluene, these are the boiling point of benzene. This is the boiling point of toluene at normal temperature. That means it is at 1 atm pressure. So this is the relative volatility, 2.34. That means it's above 1. It's possible to distillate it, okay, to separate toluene from benzene from toluene. The higher is the value, the better is the easier is the separation. For example, you have that value of 7. For hexane, a boiling point of 68.7, and p-toluene, a boiling point of 138.3. You can see the big difference in the boiling point. Then it's become easier to distill, being reflected in the relative volatility. The value is 7. It's quite high. And this for benzene, and if you compare these two, benzene and toluene is 2.34, and hexane and p-xylene is 7. So that's a big difference in terms of relative volatility. It's far easier to separate hexane from p-xylene compared to separating benzene from toluene. You can notice that the boiling point is quite a big difference too. If you look at benzene and toluene is 110.6 minus 80.1. That's the difference. If you look at hexane and p-xylene, the boiling point difference is 138.3, 68.7. That's a much bigger difference. So the lower is the value, for example, 1, it's almost 1. You can see that the boiling point is very close. 139 compared with 138. The closer is the boiling point, the harder it is to separate using distillation. The relative volatility does reflect it. You can see that it's almost 1. If it reaches 1, then you will not get any separation. In fact, this is really, it's quite difficult. It's quite difficult to separate the two of them using distillation. It's almost impossible. Okay. So that is relative volatility. So the higher is the value of your relative volatility, the easier it is to separate. That means the difference in the boiling point is very, very big. The difference of the two boiling points that you're trying to separate. They should be bigger. You can see this boiling point, 61 and 118. So you can see the relative volatility is also higher. Okay, so any question on this so far? On the relative volatility or anything earlier? Any questions? Questions?
Doctor,
Yes.
so in this distillation, we only deal with Rao's law so far, or we may also introduce Henry law.
You'll be looking at Rao's law and also relative volatility. You were looking at most of the time, excuse me, the relative volatility is mainly used in multi-component distillation. The Rao's law, just like I mentioned earlier, the data is already provided. Unless you don't have the tabulated data, then you will have to use Rao's law. Does that answer your question?
Yes, doctor. Thank you, doctor.
Excuse me. Any other questions? I spent too long on this example. Get confused because of the partial pressure and the vapor pressure. Excuse me. So if there's no question, I will stop here. We will continue looking at the distillation by next Thursday. Yeah. It's an example on relative volatility, but it's too, you can look at it yourself. Excuse me. How to calculate relative volatility? You can do that yourself. You can use Rao's law or you can use the XY value. It's either way you can do it because both of them are related in terms of partial pressure. Sorry, not partial pressure. Keep on. Yeah, this is vapor pressure. I keep on confused. Okay, guys. I will share the QR code for those that arrive late. And we will meet again on Tuesday 8 p.m. for your test 1. Guys, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, doctor.
Okay.
Thank you, Doctor. Doctor, can
Yes.
you share the appendix table, the appendix with us? Because some of our appendix, your appendix is little different with this.
Is it your appendix the same from Jane Copley's?
Yes, from John Copleys, but my appendix started with appendix 2, and some of the table that we use in the previous chapter don't have in the appendix.
See,
Especially table 10.61.
okay, I will need the appendix. Let's see. I will give it in WhatsApp then. I will put it in I will upload it in WhatsApp. Sorry, I will upload it in WhatsApp, and you can get it from there.
Okay, thank you very much, Doctor.
I do apologize for today. It's not a good start. Okay, guys.
Okay, thank you, Doctor.
Yeah.
Now, doctor,
Oh yeah.
I would like to ask you, like, regarding the test. You mentioned last time about like the one of the questions on trade tower, right?
Yes.
And the other is just humidification,
Cooling
or
tower.
like, I mean, yes. And what the cooling tower? Sorry, I mean, for the trade tower, is it like there is some, like relation? You need to refer to some, some of the other parts. Some question like you have to refer to the, like maybe the pack tower or some equations. Is it like, or just purely on trade tower?
It's the trade tower is just like the example that we look at. If you look at the example that we have gone through, it's not it's not any different from that.
Oh, all right, okay. Thank you, doctor.
Okay.